On the left, a chemical plant engineered to brute force a reaction. On the right, a microscopic ecosystem of soil bacteria processing nutrients in complete silence. This is the central tension of modern agriculture. To understand it, we have to look closely at anhydrous ammonia. At its core, it is simply one nitrogen atom bonded to 3 hydrogen atoms in a pure, water-free state. This chart shows the raw nitrogen density of common fertilizers. Anhydrous ammonia sits at a massive 82, but those atoms are locked in a triple bond that plants cannot break, meaning we can be surrounded by nitrogen while crops starve. In the early 20th century, the Haber-Bosch process solved this problem, allowing humanity to pull fertilizer directly out of thin air. It requires stripping nitrogen from the atmosphere and extracting hydrogen primarily from natural gas, a massively energy-intensive operation. These gases are then forced together under extreme conditions, up to 500 degrees Celsius and 300 atmospheres of pressure, over an iron catalyst. Today, this exact reaction is replicated on an industrial scale across the globe, feeding the centralized chemical infrastructure that sustains modern agriculture. Anhydrous ammonia is simply the raw, liquid output of this process. It skips the expensive secondary manufacturing step required to convert ammonia into a solid granule, like urea. While Haber-Bosch eliminated nitrogen scarcity, it replaced biological nitrogen fixation with a heavy reliance on fossil fuels and centralized manufacturing. Because it is a highly pressurized gas, individual farmers cannot produce or store anhydrous ammonia. They rely entirely on commercial supply chains and specialized hazard tanks. You cannot spray this on top of a field. At atmospheric pressure, the liquid instantly boils into a gas and vanishes into the air. Instead, it requires violent mechanical application. Heavy tractors pull hollow steel knives through the earth, injecting the liquid 15 to 20 centimeters below the surface. The soil must be immediately sealed shut with press wheels. Any exposed furrow allows the volatile gas to escape. For the applicator, the chemical is exceptionally dangerous. Concentrated ammonia aggressively seeks moisture, drawing water directly out of human tissue on contact. Field workers face severe occupational hazards, from deep chemical burns to airway swelling to potential blindness from vapor exposure. But these are strict handling risks. The danger applies entirely to the person operating the machinery, not to the person eating the final crop. There is a persistent myth that crops absorb toxic ammonia gas directly into their leaves and stems. They do not. The moment the gas is injected, it reacts with soil moisture, rearranging to form a stable ammonium ion, NH4+. The soil microbiome consumes this, excreting nitrate ions, NO3-. The plant roots finally absorb these ions, using them to build amino acids, proteins, and chlorophyll. When a farmer applies traditional compost or raw manure, the biological breakdown process eventually releases these exact same ions into the soil. By the time nitrogen becomes part of a grain or a piece of fruit, its chemical structure is identical, regardless of where it started.
A plant's cellular structure has no memory. It cannot tell if its nitrogen came from a high-pressure factory or a decomposing leaf. The resulting food is perfectly safe for human consumption. The actual documented threat of nitrogen fertilizers is entirely driven by improper dosage. When leafy greens are fed far more nitrogen than they can process, they accumulate excess nitrates in their tissues. In high amounts, this can cause methemoglobinemia, a serious condition affecting blood oxygen in infants. What the plants don't absorb doesn't stay in the topsoil. Excess nitrates leach downward, bypassing the root zone and permanently contaminating rural groundwater supplies. When this runoff reaches rivers and coastal waters, it triggers massive algal blooms that strip oxygen from the water, creating severe aquatic dead zones. This risk is completely agnostic to the source. Applying too much organic manure causes the exact same nitrate runoff as over-applying synthetic ammonia. Water eutrophication and nitrate toxicity are failures of timing and precision. Banning a specific chemical doesn't solve the problem if the field management remains poor. If the final nutrient is identical and the runoff risks are shared, where do synthetic and organic systems actually diverge? During heavy, repeated ammonia injection, the chemical reaction strips base nutrients and lowers the soil's pH into a highly acidic state. This rising acidity, combined with the caustic burn of the gas, suppresses microbial diversity. The living soil becomes an inert, sterile sponge. Organic inputs, by contrast, are mostly bulk carbon. They deliver nitrogen slowly, often at just 1 to 3% concentration, but they act as a structural investment. As that organic matter decomposes, it physically rebuilds the soil's architecture, enhancing porosity and allowing the earth to absorb heavy rainfall without pooling. You are feeding an entire subterranean food web. This triggers an explosion of biological activity that naturally defends crops against pathogens. Heavy reliance on synthetic ammonia forces a farm onto continuous chemical life support. Organic farming builds an autonomous, self-sustaining ecosystem. Look at this final comparison matrix. Synthetic ammonia wins on immediate speed, concentration, and short-term cost, but organic farming dominates in soil biology and handling safety, the true metrics of long-term viability. Calculations of agricultural value must account for the generational wealth stored in the soil's microbiome, rather than prioritizing immediate harvest volumes alone. Today, modern natural farming represents the most advanced, data-driven application of ecological science available to the agricultural industry. The mandate for modern agriculture rests on 3 pillars: maximizing soil health, ensuring stable crop productivity, and guaranteeing environmental protection. The future of farming relies on working intelligently with biological complexity, rather than continually trying to engineer our way around it. The JP Organic Farm ವೀಕ್ಷಿಸಿದ್ದಕ್ಕಾಗಿ ಹೃತ್ಪೂರ್ವಕ ಧನ್ಯವಾದಗಳು. ಈ ವೈಜ್ಞಾನಿಕ ವಿಶ್ಲೇಷಣೆ ಮತ್ತು ಸಂಶೋಧನಾ ವರದಿ ನಿಮಗೆ ಉಪಯುಕ್ತವೆಂದು ಅನಿಸಿದರೆ ದಯವಿಟ್ಟು ಈ ವಿಡಿಯೋಗೆ ಲೈಕ್ ಮಾಡಿ, ನಿಮ್ಮ ಸ್ನೇಹಿತರು ಹಾಗೂ ರೈತರೊಂದಿಗೆ ಶೇರ್ ಮಾಡಿ, ನಿಮ್ಮ ಅಮೂಲ್ಯ ಅಭಿಪ್ರಾಯವನ್ನು ಕಮೆಂಟ್ ಮೂಲಕ ತಿಳಿಸಿ ಮತ್ತು ಇಂತಹ ಇನ್ನಷ್ಟು ವೈಜ್ಞಾನಿಕ ಸಾವಯವ ಮತ್ತು ನೈಸರ್ಗಿಕ ಕೃಷಿ ಮಾಹಿತಿಗಾಗಿ ದ JP Organic Farm ಚಾನೆಲ್ ಅನ್ನು ತಪ್ಪದೇ ಸಬ್ಸ್ಕ್ರೈಬ್ ಮಾಡಿ. ನಿಮ್ಮ ಬೆಂಬಲವೇ ವೈಜ್ಞಾನಿಕ ಕೃಷಿ ಜ್ಞಾನವನ್ನು ಹೆಚ್ಚು ಜನರಿಗೆ ತಲುಪಿಸುವ ನಮ್ಮ ಪ್ರಯತ್ನಕ್ಕೆ ಶಕ್ತಿ ನೀಡುತ್ತದೆ. ಧನ್ಯವಾದಗಳು.